Example 2 says prove or disprove the following equations. So in order to prove that an equation holds true, we have to show that it holds true for all values. But if we want to disprove an equation, it only takes one counterexample. So for example A, we have cosine of A minus B equals cosine of A minus cosine of B. I'm going to let A equal pi over 2. And I'm going to let b equal 0. So let's see if both sides of the equation are going to hold or be the same value if we use these a and b values. So the left-hand side would be cosine of pi over 2 minus 0, which equals cosine of pi over 2. And we know that that is 0 since pi over 2 is one of our common angles on the unit circle. And then let's move on over to the right-hand side of the equation. We have cosine of pi over 2 minus cosine of 0. And cosine of pi over 2 is equal to 0, and cosine of 0 is 1. So we have 0 minus 1, which is equal to negative 1. Now notice that these two things here are not equal. Therefore, this equation is not true. Part B wants us to show that cosine of pi over 2 plus x is equal to negative sine of x. Now I'm going to start off with the left-hand side, and here we can use the sum identity. So we have cosine of pi over 2 plus x. So if we use the sum formula for cosine, we know that it's going to be cosine, cosine, sine, sine. And we have cosine of pi over 2 times cosine of x. Now remember, cosine is the opposite sign, so we want minus here, minus sine of pi over 2 times sine of x. And let's see if we can figure some of this stuff out. So cosine of pi over 2 we know is 0. Cosine of x, we can't really change that. And then sine of pi over 2, we know that this thing is equal to 1. And then sine of x, we can't really change anything there. So we're going to get 0 minus sine of x, which is equal to sine of x. And that's equal to the right-hand side. I forgot the minus sign. So minus sine of x, and that's equal to the right-hand side. So that shows that they are in fact equal. And I can write my little proof symbol. And again, sometimes it's a square, sometimes it's a shaded square, sometimes it's a little flower looking thing like what I have, sometimes you'll see QED. Any of these are totally fine. All right, so part C wants us to show that 1 plus tangent of y over 1 minus tangent of y is equal to tangent of pi over 4 plus y. I think that we should start off with the right-hand side because we can use the sum formula for tangent. So we have tangent of pi over 4 plus y, and I'm going to replace that just using the formula that we have up above. So this is going to be tangent of pi over 4 plus tangent of y divided by 1 minus tangent of pi over 4 times tangent of y. Okay, so let's see if we can do some simplification here. We know that pi over 4 on the right triangle and on the unit circle, we know that the terminal points are root 2 over 2, comma root 2 over 2, and tangent is equal to the y value divided by the x value. So in this case, that's going to equal 1. And in the bottom, we have tangent of pi over 4, which is 1 times tangent of y, and that's just going to equal tangent of y. And so this is equal to the right-hand side, and so we are done with this example. All right, so here we have some cofunction identities, and hopefully you have seen at least these two before previously. And the other ones you'll want to memorize as well. Now, example 3 is not related to the cofunction identities, but let's go ahead and talk about example 3, which says, write tangent of sine inverse of x plus cosine inverse of y as an algebraic expression in x and y only. No need to reduce the final answer. So let's ignore the tangent part right now. We have sine inverse of x, and we know that that is going to equal some angle, and I'm going to call it theta 1, and cosine inverse of y is some angle as well, and I'm going to call that theta 2. And I'm going to draw two different right triangles. So here we have angle, which is theta 1, and we know that the sine of this right triangle is x, which tells us that the opposite over the hypotenuse is x. So the opposite side length will be x, and then the hypotenuse is going to be 1. And in order to figure out what this side length is, we can use the Pythagorean Theorem. So maybe I'll just label that side length b for now. So we get b squared plus x squared is equal to 1. If I subtract x squared from both sides, and then I take the square root, we're only looking at the positive value since it's a distance or length. So this length is the square root of 1 minus x squared. And I'm going to do something similar for theta 2. So I have some, and this isn't to scale, but I have some right triangle, and cosine is equal to y. So the hypotenuse would equal 1, and so ka toa. So ka, that tells us that the adjacent side length is y, and we want to figure out this side length here. Again, we're going to use the Pythagorean theorem, and I'm just going to call that side length b. Ask me why I chose b. I don't know. Maybe I'm feeling like a bad b today. Okay, so if I subtract y squared on both sides, then I get 1 minus y squared. And then if I take the square root of both sides, I get the square root of 1 minus y squared. So this length here is the square root of 1 minus y squared. And now I want to use the sum formula for tangent, because if I rewrite what I have above, if I substitute in the thetas, then I have tangent of theta 1 plus I have tangent of theta 1 plus theta 2. And now I'm going to rewrite this using the sum formula for tangent. So that's going to equal tangent of theta 1 plus tangent of theta 2 divided by 1 minus tangent of theta 1 times tangent of theta 2. Now that we've drawn all of our right triangles, we can fill in these values. So theta 1, our tangent value, is the opposite. So this is the opposite over the adjacent. So that tells us that tangent of theta 1 is going to be x over the square root of 1 minus x squared. Then plus tangent of theta 2 will be this opposite value over this adjacent value. So that's going to be the square root of 1 minus y squared over y, all over 1 minus, and then both of these things that I wrote in the numerator, except we're going to multiply them together. And remember that it says that we don't need to reduce our final answer, which is really nice because this is a very ugly fraction. So it's nice that we don't have to simplify that at all or rationalize the denominator. However, you do want to get good at problems like these because you will need to do algebraic manipulations and trig manipulations like this once you reach calculus. So that concludes example 3.